In this video, we'll talk about what makes a good leaving group. So for a substitution reaction or an elimination reaction, there's going to be a group that has to leave. And so that can really impact the rate of a reaction. So a good leaving group is going to polarize the carbon leaving group atom bond. So electron density will be shifted away from the carbon, making it more electrophilic, and towards the leaving group. And so then the nucleophile can come in and attack because it'll be attracted to that electrophilic carbon atom. So leaving groups tend to be electronegative so that they can pull electron density away from the carbon atom and towards themselves, therefore polarizing the bond. And then secondly, a good leaving group is stable once it's left. So if the leaving group left and it was very reactive, it would just jump back on, and then the reaction wouldn't go forward. So good leaving groups are generally weak bases. So anything that would be a strong base would be a very poor leaving group. So we'll go to the next page and do some examples. So some of the common good leaving groups are the halogens that are larger, so Cl-, Br-, I-. These are all large atoms that are able to withstand a charge easily because they have so much surface area to spread the charge out over. And they're also electronegative. They're at the end of the periodic table, and so they can handle that negative charge. If you had a water attached, it's positively charged, so when it leaves, you would just get neutral water molecule, so that would also be a good leaving group. So water is a good leaving group. Ammonia is a good leaving group because upon leaving, if they're attached to something, they would become neutral. They would be positively charged while attached to something. And then lastly, a good leaving group stabilizes the transition state. So what this basically gets down to is size. As we have leaving groups that are larger, they're more polarizable, and so they can stabilize that transition state as the leaving group is leaving. So when we have this bond, we get a partial negative here and a partial positive there. So what ends up happening is that this X has all this electron density, and it can sort of spread that electron density out like this so that it's still kind of attached to that carbon atom, and this is that ability to polarize. And so it's breaking that bond, but that electron density is lingering a little bit longer and further stabilizing that carbon atom while the leaving group is leaving. So this really comes down to size, and the larger X is, the more polarizable. And it is this polarizability that allows for the transition state to be stabilized.